We have given here the one I section beam, which one is also called as W beam. Dimensions are not given, but he has said the centroid location is 80 mm measured upward from the bottom edge of the stem, and the moment of inertia is given, that is Iz is given, and we have given here a overhang beam, and we have support at A and the support at D. We have a one couple is acting in anti-clockwise direction, that equal to 4 kN meter, and one value of UDL is acting between D and E, whose span equal to 2 meter, and the UDL value is equal to 2 kN meter. Determine the maximum tensile stress on a cross section just to the left of B. So one point you have to consider on the left hand side, and other point you have to consider on the right hand side. So you have to calculate the bending stress just to the left and just to the right, means you have developed two FBD of the beam AB. One is to the left and one is to the right, but before that you have to find out reaction at A. That can be obtained by taking the moment about the other support, that equal to D. So this one is the centroid, and we'll represent the centroid by G, and the distance of centroid from bottom is y bar, and this value of y bar is given to us is equal to 80 mm. So we have y bar is equal to 80 mm, and the value of Iz is given. We have Iz equal to 13.4 into 10 to the power 6 mm to the power 4. So first of all we'll find out here reaction AY, and one reaction we have dy. So we have one support at A, other support at D. We are interested in AY for quick calculation. So we'll take the sum of moment of all forces about the other support equal to D, and we will use here the clockwise moment. So whether you want a clockwise or anti-clockwise, that you decide first. According to that we have to make our sign convention. AY about D will make a clockwise moment. Since the clockwise is positive, so value of AY will be taken as positive. Perpendicular distance between point A and point D is 2 plus 1 plus 1, that equal to 4. This value is a couple, and this couple is anti-clockwise, so will be taken as a negative value. So instead of 2 here, I will make here 1 kN meter, and equivalent of this load will be same as equal to W multiplied by L. So we'll show here equivalent load, that equal to W into L is same as 1 into 2, that will be kilonewton, and this load from the point D will act the halfway of 2, that equal to 1 meter. So the last term here will be this load, that equal to 2 kilonewton, will make a clockwise moment is positive, is 2, and the distance between this equivalent point load from the point D is equal to 1 meter. So we have minus 4 plus 2 is equal to 2 on the right hand side, 2 divided by 4. So in this case we get the value of AY is equal to 2 divided by 4, that equal to 0.5 kilonewton. Now first we calculate here the maximum tensile stress on a cross section just to the left of B. When we say the left of B, then we'll not show the moment. Since we are interested at B, we'll consider the FBD for the beam AB. In that case we have to show the reaction here. This reaction is same as equal to AY, and the value of AY come out to be 0.5 kilonewton. Length of this beam will be same as equal to 2 meter. So this distance equal to 2 meter, and we are slightly on the left hand side of B. So this one is same as our point B. But we will not show the couple acting at point B. Couple acting is on the right hand side. Here we'll show one shear force is acting downward. Now I will represent this value of shear force equal to VB minus. Minus means on the left hand side. And we'll assume here one reaction, that equal to MB, and also I will write this value as a B negative, means we are on the left hand side of the B negative. So using the equilibrium equation we can find out the value of MB. So for this purpose we have sum of moment of all forces about point B, and this time we'll take the anti-clockwise positive. So this one is anti-clockwise, anti-clockwise is positive, must equal to 0. Moment of AY about point B is a clockwise and anti-clockwise is taken as positive. So AY is clockwise is negative, is 0.5, and multiplied by the distance equal to 2 meter. The couple acting at point B, that is the bending moment at point B, is acting in an anti-clockwise sense, so that will be taken as positive value. So we have positive value of B on the left hand side must equal to 0. It means that we have bending moment acting on the left hand side of B is equal to 0.5 into 2, that equal to 1 kilo Newton meter. If we consider the point here at A, which one is the top fiber, and point B is at the bottom fiber, here the value of M already come out to be positive, and we want the positive value of tensile stress. So positive value of tensile stress we can obtain if we select the value of Y is negative. So bending stress at the bottom fiber B will be equal to minus M into YB. This time we have this value is YB, and value of YB is same as 80 but negative, and therefore negative negative become positive, divided by IZ. So we have minus 1 kilonewton is minus 10 to the power 6. Value of YB you have to take is negative, is minus 80, divided by IZ. IZ is 13.4 into 10 to the power 6. So this will give you positive value. Positive means tensile. So bending stress at point B is a tensile is come out to be 5.97, that will be megapascal if we are on the left hand side. Now we'll consider the right hand side. In that case the additional value of 4 kilonewton meter will come, but will come in anti-clockwise sense. So in the second part we'll consider the AB plus, means we have to include the additional load equal to 4 kilonewton meter. So let's mark the point A and point B. Point B is positive. Positive means we are on the right hand side. At point A we have vertical reaction is AY, and this reaction is same as equal to 0.5 kilonewton. Already we have done this. The distance AB is same as equal to 2 meter. Since we are on the right hand side, we'll show here one couple acting, and this couple acting is anti-clockwise sense, and the magnitude of the couple is 4 kilonewton meter. At point B plus, we'll show here one reaction, that is the shear force is acting is VB positive. Positive means on the right hand side, and we'll show here one couple acting. We assume the couple is anti-clockwise, so we'll take this value as MB positive. Now to find out the value of MB positive, we'll again use the equilibrium equation. This time we'll take the sum of moment of all forces about point B. And since we have taken this value anti-clockwise positive, so we'll take the anti-clockwise positive. So don't get confused. You have to assume here first whether clockwise is positive or anti-clockwise is positive. If you assume anti-clockwise is positive, answer is come out to be positive, then this direction is correct. Otherwise you have to reverse the sign. So the moment of AY about point B is clockwise. Clockwise is negative, and we have AY equal to 0.5. Perpendicular distance between A and B is equal to 2. Couple is shown here, which one is 4 kilonewton is anti-clockwise. Anti-clockwise we have to take is positive. MB you assume is anti-clockwise, so that also you have to take as a positive value. On the right hand side we have equal to 0. So we can find out here what is the bending moment on the right hand side of B. That will be equal to, we have minus 1 plus 4, that equal to plus 3. On the right hand side it will become minus 3 kilonewton meter. Now whenever the answer is come out to be negative, it means that you have to change this direction. So we have MB acting is equal to 3 kilonewton meter and is clockwise. Clockwise means hogging. And whenever we have a hogging, in that case this value you have to take as a negative value. So you have to treat the value of M as negative value is minus 3 kilonewton meter. Now in general the bending stress distribution is a function of Y is given as minus M into Y divided by I. Now remember here the value of M is negative and negative become positive. It means that you have to select the value of Y is positive. This time the point A is above the centroid, so value of Y will be positive value and is same as equal to 80. Here you have to put the value of M equal to minus 3 kilonewton meter, and IZ is same as 13.4. So it will guarantee positive value. So we have minus 3 into 10 to the power 6. This one is minus value. Into y is equal to 80 divided by iz. So we have iz equal to 13.4 into 10 to the power 6. So this time on the top fiber we are getting the maximum value of a bending stress. So we are maximum value of a bending stress, but in tensile in nature is come out to be 17.91, that will be megapascal. On the left hand side at point B we have the tensile stress, and when we are on the right hand side, then at point A we have the tensile stress. The tension flange of a cast iron I-section beam is 240 mm wide and 50 mm deep. So this one is the bottom flange, which one is 240 mm in wide and 50 mm deep. He said that it's a tension. It means that we have a tensile stress in the bottom flange. The compression flange is 100 mm by 20 mm deep. So top flange here is in compression. So on the top fiber we have compressive stress. Find the load per meter run in kilonewton per meter, that is UDL we have to find out, which can be carried over by 4 meter span of a simply supported beam. So we have a simply supported beam, span is equal to 4 meter. UDL, that is the value of W, we have to calculate. The maximum permissible stresses are 90 megapascal in compression and 24 megapascal in tension. The moment of inertia is given here. This value you have to treat as a z-axis. That is the moment of inertia about the z is 351.06 into 10 to the power 6 mm to the power 4. And the centroid is a distance of 122.6 mm from the bottom flange. So this one is the unsymmetrical I section. The value of centroid is given from the bottom edge. This value is given about the centroidal axis. So centroid will lie on this vertical symmetrical axis. So exactly at this point we have location of centroid, let represent by G, and this one is the value of y bar, and the y bar from the bottom edge is at a distance equal to 122.6 mm. We have a compressive stress on the top flange and the tensile stress in the bottom flange, but which value is a valid value, that you have to first identify. So either we assume here that the 90 megapascal will attain in the compression, then we can find out the value of the stress in the bottom flange, which one is tension. Or otherwise we can assume that in the bottom flange the tensile stress attained equal to 24, and from that we'll find out the value of compressive stress. That value must be less than 90. So this position represents here the neutral axis, and we'll assume here that in the bottom flange we attained a value of tension is equal to 24 megapascal. So at bottom fiber here we'll assume that the tensile stress attained is 24 megapascal. Tensile will show rightward. So we'll show this arrow here, which one is representing the tension at the bottom. So let's mark here the bottom point equal to B and the top point will be equal to A. So this value corresponds to sigma B is the maximum tensile stress in the bottom flange, and that is equal to 24 megapascal. So this value is same as 24 megapascal. And at point A, which one is the top fiber, we have compressive stress. Now whatever this value of the compressive stress will come at point A must be less than the permissible value, that equal to 90 megapascal. Then our assumption is valid. So as far as the bottom fiber is considered from neutral axis, that is from G, at a distance equal to 122.6. So we have YB value will be negative value because it is below the center of gravity, is 122.6 is mm, and this value represents the YA value, that is the top fiber. Total distance is 300 plus 50 plus 20 minus y bar. 350 is 350 and plus 20 is 370. So we have 370 minus 122.6. So this distance is YA, and the YA come out to be 237.4. 237.4, that will be mm. Using this we can calculate the stress at point A by similar triangle, and we'll confirm here this value is less than 90. Now the bending stress sigma b, which one is a function of y, is given as minus m divided by I multiplied by distance y. M and I remain same for the given cross section. It means that the bending stress is proportional to negative of y. So we have bending stress at point A divided by the bending stress at point B will be equal to minus of y divided by minus of yb. Minus and minus sign will get cancelled here. Bending stress at A you have to find out. So we have sigma A. Bending stress at B is a positive value is 24. Ya is a positive value is 237.4. Negative sign is already cancelled out. Divided by yb value is negative 122.6. So if you follow the standard procedure, automatically the value of sigma bending at point A will come out to be compressive nature. So this value of bending stress at point A is come out to be minus 48.3, and this value is less than 90. It means that this is a valid assumption. So this one is 90 megapascal, means assumption is valid. So out of the top and bottom, we have maximum value of the bending stress is at the bottom. So we have maximum value of a bending stress, that is sigma b maximum, is same as the bending stress at point B, that is equal to 24 megapascal. Design is based on 24 megapascal, that is tensile in nature. Okay, all right, we got the bending stress. Now the second part is that we have simply supported beam, and for that beam we have to calculate the value of UDL. So that part we'll discuss in the next slide. Now there is no need for this discussion, only this answer is required, that is the bending stress maximum is required, that is equal to 24 megapascal. Because already the value of y is known to us, that is the value of yb is known to us, value of I is known, we are interested to know the value of m, that is the maximum bending moment, and for the given UDL we'll calculate the maximum bending moment. I will collect the value of Iz also. We have Iz is same as equal to Ixo is 351.06 is 10 to the power 6 and is mm to the power 4. In addition to this, I require the value of y. The value of yb will required actually, because we are interested at point B. Yb is equal to minus 122.6 mm. So let's consider here a simply supported beam whose span is equal to 4 meter, and we have UDL whose intensity equal to W is kilonewton per meter. So for 1 kilo we have 10 to the power 3 Newton, and for 1 meter another 10 to the power 3 mm. So it is equal to 1 Newton mm. 1 Newton mm is same as equal to 1 kilonewton meter. Now because the UDL is spread over the length equal to 4 meter, so total load will be equal to W into L, and we have reaction at point C will be equal to WL divided by 2. Because of the symmetrical loading, we have reaction at point D is also equal to WL divided by 2. Now reaction at point C is WL by 2, so you have to move vertically upward by WL by 2. So this value is same as WL by 2. Total load equal to WL, and this one is a UDL. So if it is load is a rectangular, you will get a triangle in SFD. So this total vertical distance is WL, and therefore we left here with minus WL by 2. So we have WL by 2, but negative value, and the reaction at D is same as WL by 2. So finally we'll close at D equal to 0. This length is same as equal to L by 2. So we have L by 2 is equal to 2 meter, and this length is also L by 2 is equal to 2 meter. So area of the SFD diagram will represent here the change in the bending moment diagram, and the area of this triangle is same as equal to 1 by 2 WL by 2 into L by 2. So this was generalized expression I am using for UDL. Next time we will not prove it, we will just use the direct equation. The bending moment at the support C and at D is always equal to 0, and here we have a change in the shear force sign, and therefore maximum bending moment at point E, and we have a triangle, so we will get a parabola here with a downward slope. So we'll have to construct here a downward parabola. So exactly at point E here, we have maximum value of bending moment is same as equal to 1 by 2 multiplied by the height of the triangle is equal to WL by 2, and we have width is equal to L by 2 is WL square by 8. So in this case, the maximum bending moment will come out to be WL square divided by 8. So this equation you have to remember, whenever we have a UDL in a simply supported beam over the entire span, the maximum value of bending moment is WL square by 8. So we'll have our flexure formula. Sigma By will replace as sigma B maximum. So we have sigma B maximum value. Minus sign will be as it is. Maximum bending moment is W into L square divided by 8. And we have value of Y is YB is equal to minus 122.6 mm and is divided by IZ. Value of IZ is 351.06 into 10 to the power 6. Here the maximum bending stress you have to put as equal to 24 megapascal is equal to minus become plus. We have constant is 122.6 divided by 8 divided by 351.06 into 10 to the power 6. Further we have L square. We have total length is equal to 4 meter. So it will be equal to 4000 square multiplied by UDL equal to W. So we can solve this value of UDL, and from this we will get the value of UDL, that is W equal to approximately this answer is 34.36 Newton per mm. And already we have shown that 1 Newton per mm is kilonewton meter. So we have same answer is kilonewton meter, that is 34.36 kilonewton meter. Next time remember that if we have a UDL, maximum bending moment on the simply supported beam will be WL square by 8. So using the tensile stress, which one is the maximum value we have considered equal to 24 megapascal, we have obtained the value of W equal to 34.36 and we have maximum bending moment equal to WL square by 8. Now we have to confirm here that if we use the value of maximum bend equal to 24 megapascal and we have the maximum value of the bending moment, that is M is equal to WL square by 8, and we obtain the value of W, that is a UDL equal to 34.36 Newton per mm. So whether our method is correct or wrong, for this one what we'll do, we'll check out the stress at point A and we'll confirm here this value is less than 48.3, then our calculation procedure is correct. So let's calculate here what is the bending stress at point A. So we have a same formula again, that is minus M divided by I multiplied by Y, but this time it's a YA. So minus M is same as WL square by 8. This value is same as minus and WL square by 8 multiplied by YA divided by I. So we have negative. W is same as equal to 34.36. Length L you have to take as a 4 meter is 4000. You have to make a square of it. YA value is same as equal to 237.4 divided by 8 times IZ, and we have IZ is 351.06, 10 to the power 6. Here the maximum stress sigma A will come out to be 46.47, which is less than 90 as well as less than 48.3. So that is the correct answer. It means that our assumption is valid. So this one is less than 90. It means that the failure will be always at the bottom, that is the 24, which one is the lower value at the bottom as compared to 90 megapascal at the top. The video you are watching is from the app, which is the More Class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.